An enemy radar locks a missile onto an SR-71 Blackbird over Vietnam. The pilot doesn't dive, doesn't dodge, doesn't pop flares. He just speeds up, and it works. Every single time. Stick with me and you'll know the 5 things hiding under this plane's skin that made that possible. Because honestly, I think this is the most over-engineered machine anyone's ever gotten off the ground. Quick context. The SR-71 entered service in 1966. It's a spy plane. No bombs, no guns. Its only defense is altitude and speed. Mach 3.2, over 3 times the speed of sound, cruising at 85,000 feet. High enough that pilots could see the curve of the Earth and the black of space above them. And here's a detail people miss. At that altitude, a cabin failure would kill a pilot in seconds. So crews flew wearing actual spacesuits, the same style NASA used. This wasn't a plane. It was closer to a spacecraft that happened to take off from a runway. Its cameras, from 80,000 feet, could resolve detail on the ground the size of a license plate. And if it ever went down over enemy territory, there was no rescue plan. Pilots flew every mission knowing that. It also took 2 people to run, a pilot up front and a reconnaissance systems officer behind him, working the cameras and sensors, since there was simply too much happening at Mach 3 for one person to fly the plane and run the mission at the same time. Here's the weird part, though. Some of the missiles fired at this plane, and it was fired on more than once, including a documented run over Libya in 1986, where Libyan SA-5s went up after it, could actually fly faster than it. In a straight line, sure, but they couldn't match its range, and they definitely couldn't match what it could do at altitude. A missile built to chase a predictable flight path has nothing to work with once that path bends away from it at 85,000 feet. Speed and altitude weren't just stats, they were the whole defense system. By the end of its career, more missiles had been fired at this one aircraft than any other plane in history, not one of them ever connected. That's thing 1. It's also the one most people already know. The next 4 are why it actually worked. So, keeping a plane at that speed for an hour straight. That's a problem nobody had solved. Lockheed's Skunk Works, the same secretive team behind the U-2 spy plane, took this one on knowing full well that normal jet engines aren't built for supersonic air slamming into the inlet. Feed one that fast and it stalls. Chokes. Flames out. And that's exactly the job this engine had to survive. Over and over, for an hour between refuelings. Refuelings that happened mid-air, from tanker planes flying almost as fast as they could go, because nothing slower could keep pace long enough to hand off fuel. The engine itself, the Pratt & Whitney J58, was just a turbojet, a good one. But on its own, it only made about 17.6% of the thrust needed to cruise at Mach 3.2. Not top speed, cruising speed. So where did the other 82% come from, without inventing a whole new kind of engine? Kelly Johnson's team spent years on this exact problem, burning through wind tunnel hours on a plane that, on paper, shouldn't have been buildable yet. They turned the jet into something closer to a ramjet, mid-flight, without ever landing to rebuild it. A ramjet has no moving parts. It just rams air in, lights it, and shoots it out the back. Great at high speed, useless from a standstill. So they built a hybrid instead, a turbojet to get moving, and a set of sliding inlet spikes and bypass doors that quietly rerouted air around the turbojet core as the plane sped up. So the faster it flew, the more it acted like a ramjet. Thing 2. Picture a cone at the front of each engine, sliding back and forth by over 2 feet. That's the inlet spike. Its whole job is holding a shock wave, a wall of piled-up supersonic air, in exactly the right spot. Below Mach 1.6, it sits forward. Past that, it inches backward for every tenth of a Mach gained, all the way to Mach 3.2, with an onboard computer checking and correcting its position dozens of times a second. By cruise, this spike is doing more than half the plane's total thrust. The engine's basically along for the ride at that point. But get it wrong, and it's bad. A gust, a bad yaw, one mistimed door, and the shockwave slips. Pilots called it an unstart. Up to 70% of an engine's thrust, just gone, in a fraction of a second. The plane snaps violently to one side, hard enough to crack a pilot's helmet into the canopy, while the onboard computer scrambles to shove the spike back into place. Early models unstarted so often that Lockheed had to add an automatic system just to catch it, because a human reacting on instinct wasn't fast enough to save the flight. That constant self-correction is exactly what made this plane so hard to hit. It wasn't doing one fixed thing at one fixed speed. It was reshaping itself in real time, in ways no missile computer of that era was ever built to predict. Outrunning a missile was never about raw speed. It was about moving inside an envelope nothing else could follow into. And here's the part that shouldn't make sense. This plane got better fuel mileage the faster it flew. A machine built entirely around brute force ended up being most efficient right at the edge of what it could do, which meant outrun the missile, cost it nothing extra. It was just what the plane was already best at. But fixing the engine created a bigger problem. Flying this fast turned the whole aircraft into a slow-motion furnace. At Mach 3.2, the nose hit around 300 degrees Celsius. The engine bays got hotter, over 300 up front, close to 6.5 in the back, hot enough to warp or melt most aircraft skins. And the heat did something stranger on the ground. The airframe was built with panels that didn't fit tightly at room temperature, on purpose, because titanium expands as it heats. Fuel actually dripped out of the wings while it sat on the runway. It only sealed itself once it got up to speed and the metal expanded into place. Quick comparison too. The Concorde flew at barely half this speed, and it was once painted blue for a Pepsi campaign. They had to slow it down afterward, because the paint alone was soaking up too much heat from the sun. And the Concorde's made of aluminum, same as every airliner today. Aluminum gives up its strength long before SR-71 temperatures. That's a big reason the Concorde never got past Mach 2. If Lockheed couldn't solve this, none of the engine work would matter. The plane would cook itself before it ever got the chance to outrun anything. The fix was titanium, 93% of the airframe, and on paper, that's a nightmare. Way more expensive than aluminum, brutal to machine, it even reacts badly with open air mid-weld. Here's the part that still sounds made up. America didn't have enough high-grade titanium ore of its own to build this plane, so the CIA quietly bought it through shell companies, from the one country with the supply they needed, the Soviet Union. The plane built to spy on the Soviets was partly made from Soviet metal, and the Soviets had no idea. Even handling the stuff was new territory. Early titanium batches kept turning up brittle for no clear reason, until someone traced it back to the felt-tip pens workers used to mark measurements on the sheets. Trace chlorine in the ink was enough to weaken the metal. After that, every marking pen on the factory floor got swapped out. But titanium has one trick. Nothing else has. Its internal bonds just refuse to break down under heat. Real strength past 600 degrees. Barely any expansion once it's already hot. For a skin sitting next to 650-degree engine bays, that wasn't a nice to have. It was the only material on the table. Thing 3. Now, here's the detail that seems to break its own logic. This plane was painted matte black. Airliners go white to reflect heat and stay cool. So why paint a plane that already runs hot in the color that absorbs the most heat there is? There's an actual law of physics behind it. Kirchhoff's law. Whatever's best at soaking up heat is just as good at throwing it back off. Up at 85,000 feet, the heat coming off this plane's own skin, just from slamming through the air, completely dwarfed anything the sun was giving it. So the black paint wasn't there to block sunlight at all. Think of it like a cast iron pan versus a shiny one. The dark, rougher surface actually radiates heat away faster once things get hot enough. It's just usually the sun doing the heating, instead of the plane's own skin. Here, the plane was the heat source, so black became the smarter color to wear. It was there to help the plane dump its own heat faster than it built up. It did double duty, too. That paint was mixed with iron ferrite particles that helped soak up radar waves instead of bouncing them back, making the plane harder to paint a lock on in the first place. Same coat of paint, 3 jobs: cooling, camouflage, and stealth. Thing 4. Even the fuel got in on it. The SR-71 ran on a blend called JP7, stable enough that it wouldn't ignite from surface heat alone. Stable enough, in fact, that you could drop a lit match into a bucket of it, and the match would just go out, which meant regular engine igniters couldn't light it either. Lockheed had to inject a separate chemical, triethylborane, that bursts into flame the instant it touches air, just to get the engine lit in the first place. But that same stubbornness meant the fuel could double as a coolant, running through the airframe first, pulling heat out of the oil, the hydraulics, the electronics, before it ever reached the engines to actually burn. This plane wasn't just resisting heat, it was pumping it out of itself, using the one fluid it already had to carry by the ton. Thing 5. 5 systems. 1 goal. A hybrid engine that faked being a ramjet. A cone that held a shockwave in place by inches. Skin built from the very country it was spying on. A paint job that broke its own rules on purpose, 3 times over. And fuel too stubborn to burn, doing double duty as its own coolant. None of this came cheap either. A single sortie could burn through tens of thousands of gallons of fuel and needed its own dedicated tanker just to make it home. Plus a ground crew to suit the pilots up like astronauts before they even reached the jet. Keeping this plane flying was practically its own small air force. The Air Force retired it in 1990, not because anything caught it, but because satellites had quietly taken over the job it was built for. It got a brief second life in the mid-90s. Then NASA flew a couple for a few more years after that, mostly just to see what else the airframe could teach them. On its last Air Force flight, one SR-71 flew coast to coast, Los Angeles to Washington, in just under 68 minutes, a speed record that still stands today. It had flown over some of the most heavily defended airspace on Earth. Missiles came at it more than any other aircraft in history. Not one was ever shot down. Because every missile fired at an SR-71 wasn't really racing a plane. It was racing an engine that shouldn't have worked, a metal that shouldn't have belonged there, and a paint job that broke its own rules on purpose. And it was losing that race before it ever left the launch rail.